All right, I just want to run through basically what we left off with at the end of last class, which was how to possibly figure out PDFs, so probability density functions, for sums of independent random variables. All right, so just to remind you where we left off with x and y being independent continuous random variables, and we asked this question, which was, if we look at the sum x plus y, that's going to be another random variable, and that means that we should be able to figure out its PDF, its probability density function. And so what we want to do here is ask the question, how do we compute this PDF for the sum, which is going to be, just using our standard notation, f sub x plus y, right? That's the random variable that we're trying to find the PDF for. So how do we compute this? Well, the way that we go about it is a way that we've done many times in the past. What we're going to do first is, instead of considering the PDF by itself, we're instead going to consider the CDF, the cumulative distribution function. So consider the CDF using our standard notation. That's going to be capital F of x plus y, and we're going to evaluate this at some arbitrary value a. So just by the definition of what this is the probability that x plus y, the random variable for which we're evaluating the cumulative distribution function, the probability that x plus y is going to be less than or equal to a. And now what we pointed out in class is that this is a joint condition on both x and y. All right, so this is a joint condition on x and y. So that means that we could write this down as a double integral using the joint PDF for x and y, right? So the joint probability density function. And so that's what we do. We say this is the double integral over the region where x plus y is less than or equal to a, and it's the double integral of the joint PDF f sub x comma y, as opposed to f sub x plus y, which is what we're trying to figure out. And this is going to be evaluated at xy. It's a double integral, so it's dA. Now, this is where we're going to use, essentially, this independence of our random variables, right? If you remember, what this means is that we're going to say our two variables are independent if their joint PDF can be factored, right? So this thing evaluated at xy, if this factors nicely into f sub x of x times f sub y of y. All right, so we're going to use that right here in the next line. This is the same thing as saying it's the double integral over the region where x plus y is less than or equal to a, and we're going to use the fact that this factors into f sub x evaluated at x times f sub y evaluated at y. And now the reason why this is so nice is that when we're calculating double integrals like this, first we're going to turn it into an iterated integral, first with respect to x or y, whichever one we choose to go first, and then with respect to the other variable second. And when we're evaluating iterated integrals of functions of multiple variables, say we're integrating with respect to x, well then we treat everything involving y as a constant. And so knowing the fact that this joint PDF can be factored by independence into a product just of something involving x times just something involving y, this is going to enable us to say some really nice things about the integral. And so what we're going to do here I'll carry on with this calculation over here. Well, we want to write down this region in a way that we can split it up and say, okay, x is going to go between these two bounds and y is going to go between these two bounds, so that we can then write this double integral instead as an iterated integral. So the thing to observe here is that let's solve for y maybe. So this is the same thing as saying that y should be less than or equal to a minus x. And that means that since this is all y values which are going to be less than or equal to a minus x, it's the same thing as saying that y should go between negative infinity and a minus x. And now x is going to be the thing that necessarily is independent, is free as a variable, not as a random variable in this case, but just as a regular old calculus variable. And so negative infinity should be less than x, should be less than infinity, right? This is the variable that we have to allow just to range freely. And once we have this, we can rewrite this double integral as an iterated integral. So this will be the integral from x is negative infinity to infinity. Of course, saying x equals negative infinity isn't, the most exactly appropriate thing to say, but it's just to indicate which integral's which. And the inside integral would be y from negative infinity up to a minus x. All right, and this is, the integrand hasn't changed at all. This is still the PDF of x evaluated at x, PDF of y evaluated at y. And now we have an order for our integrals. Let me get rid of this stuff in blue here. We have an order for these integrals now. We integrate y first and x second. So this is going to be dy dx. All right, and now this integral here, right, the integral of f sub x of x times f sub y of y dy, well, what this means is that I can treat all of this stuff, which is sort of factored out from the function involving just y. We can factor all this stuff out that just involves x out in front of the entire y integral, right? This is really why this is nice. So all of this, let me use a different color here, all of this comes out in front of the y integral, right? So this is really the integral from x is negative infinity to infinity, f sub x of x times the integral from y is negative infinity up to a minus x, f sub y of y dy. And now the only thing we're missing is our dx outside of everything, right? So we really have this, right? The fact that our two random variables are independent means that they're joint PDF factors, and that means that we can really factor the integration as well. And that's what makes this so useful. Because now, this thing in the parentheses in here, well, we know what this is. It's got a name, right? This thing is the CDF, capital F sub y, evaluated, right? The CDF for y is going to be the integral from y is negative infinity up to whatever this upper bound is. So that's going to be where we evaluate our CDF. So this is the CDF of y, which is capital F sub y, evaluated at a minus x. And so this lets us rewrite our integral just as an integral of things involving x, right? Y, all mentions of y will be gone except for the fact that we're going to use the CDF for y. Right, so what we get here is the integral from negative infinity to infinity. I don't need to specifically mention that it's x values anymore because, well, this is just going to be a one-dimensional integral. And we're going to have f sub x, lowercase f, that is. So the PDF for x multiplied by the CDF for y, evaluated at this strange place, a minus x. So we have this. And this is, sort of all well and good. The question is, what do we actually do with this, right? So I mentioned in class that this is an example of a convolution. And as the name suggests, convolutions are quite convoluted to actually calculate with. But the idea here is that we have the following fact. All right, we know that the CDF, so the cumulative distribution function for the sum of x and y, evaluated at A, is going to be equal to, by all of this work we just did, right, cutting out all the middle parts of the calculation and just jumping to the punchline, we get that it's equal to this. And there's a dx tagged on at the end of that. So the question now is, what the heck do we do with this, right? How do we actually calculate anything with this in sort of not only a nice way to write down so that it's really nice and clean looking, but also in a way that's convenient for us to actually calculate with by hand. So that's what we're going to talk about next.